Dear students, we will now discuss about measures of dispersion. After going through this module, you will be able to explain the concept of dispersion, compute numerical quantities that measure the dispersion of a set of data, compute the coefficient of variation, and find a measure for concentration of certain distribution of data. Measures of dispersion allows us to numerically describe the scatter or spread of measurements. Among the measures of dispersion discussed here are the range, quartiles, variance, and standard deviation. The subject to be discussed are concepts, range, variance, standard deviation, concepts. Dispersion is used to denote the degree of heterogeneity in the data. It is an important characteristic indicating the extent to which observations vary amongst themselves. The dispersion of a given set of observation will be 0 when all of them are equal. The wider the discrepancy from one observation to another, the larger would be the dispersion. A measure of dispersion is designed to state numerically the extent to which individual observations vary on an average. Dispersion indicates the scatter or variation in the values of a series. As a statistical measure, it is used as a measurement of variation, such as in quality of product, income distribution, economic development, etc. Measures of dispersion or variability are concerned with describing the variability among the values. Several techniques are available for measuring the extent of variability in data sets. Important measures of dispersion are the range, variance, and standard deviation. Let's now discuss about range. Of all measures of dispersion, range is the simplest. It is defined as the difference between the largest and the smallest observations. Notice that for group data, the largest and smallest observations are not identifiable. Hence, we take the difference between two extreme boundaries of the classes. It is intuitive that because of the central tendency, if one selects a small sample, observations are more likely to be around its mode than away from it. Less likely or extreme values will be included in the sample when its size is large. This, in other words, implies that range will increase with increase in sample size. Also, it is known that in repeated sampling with small sample size, range varies considerably, making it a less suitable measure for comparisons. However, range is a measure which is easy to understand and can be computed quickly. In descriptive statistics, the range is the length of the smallest interval which contains all the data. It is calculated by subtracting the smallest observation, that is the sample minimum, from the greatest, that is the sample maximum, and provides an indication of statistical dispersion. It is measured in the same units as the data. Since it only depends on two of the observations, it is a poor and weak measure of dispersion, except when the sample size is large. For example, in the data A, B, C, the range is C minus A. Find the range in 3, 5, 7, 3 and 11. Step 1. Arrange the numbers in ascending order, that is 3, 3, 5, 7 and 11. Step 2. In the above distribution, the largest number is 11 and the smallest value is 3. Formula for ranges: largest number minus smallest number. Therefore, the range is 11 minus 3, that is 8. The range, in the sense of the difference between the highest and lowest scores is also called the crude range. When a new scale for measurement is developed, then a potential maximum or minimum will emanate from the scale. This is called the potential range. Of course, this range should not be chosen too small in order to avoid a ceiling effect. When the measurement is obtained, the resulting smallest or greatest observation will provide the observed range. The middle range point or the mid-range point, that is the point halfway between the two extremes, is an indicator of the central tendency of the data. Again, it is not particularly robust for small samples. The advantages, it shows the spread of the results, and the disadvantages, it does not take into account any clustering of results in a set of data. It is affected strongly by outliers, that is very high or very low results. Let us now discuss about interquartile range. Range as a measure of dispersion does not reflect a frequency distribution well, as it depends on the two extreme values. Even one very large or small observation away from general pattern of other observations in the data set makes the range very large. For example, when the range is found to be excessively large because of the presence of very large one observation, and to avoid such extreme observations, particularly when there is a strong central tendency, interquartile range is useful as a measure of dispersion. It is defined as interquartile range is equal to Q3 minus Q1, that is P75 minus P25. Interquartile range is the range of the middlemost 50% of the observations. If the observations are compact around the median, that is, a strong mode close to the median exists, interquartile range will be smaller than half of the range. If the data are flat, having no central tendency, this measure will be large and its value will be close to half of the range. The interquartile range, the IQR, is the distance between 75th percentile and the 25th percentile. The IQR is essentially the range of the middle 50% of the data. Because it uses the middle 50%, the IQR is not affected by outliers or extreme values. The IQR is also equal to the length of the box in a box plot. Example, compute the interquartile range for the following data: 18, 33, 58, 67, 73, 93 and 147. The 25th and 75th percentiles are the second and sixth observations respectively. IQR is equal to 93 minus 33, that is 60. The interquartile range is 60. Advantage is that it ignores extreme values and it is easier to use than the range when comparing data. Now, let us move on to variance. The most frequently used measures of dispersion are variance and standard deviation. Variance is so commonly used that it is also called dispersion. Variance is a measure which suitably combines individual deviations from the mean, treating each observation with equal weight as in mean deviation. For variance, however, measure of individual deviation is taken as the square difference from the mean. Since it is more manageable to use the square difference rather than absolute difference, particularly while doing formal mathematics, use of variance has become more popular. Conventionally, variance is denoted by sigma squared. Variance is defined as the mean of the square deviations of observations from their mean. The variance is similar to the mean absolute deviation in that it is based on the difference between each value in the data set and the mean of the group. It differs in one very important way. Each difference is squared before being summed. For a population, the variance is represented by V into X, or more typically by the lowercase Greek s squared. The formula is variance, that is X or sigma square, is equal to sigma X minus mu the whole squared divided by n. Most statistical methods deal with or include the concept of variance. Variance is the variability in certain traits in population of interest. Throughout statistical textbooks, you will find the concept of variance and the concept of standard deviation coupled. This is because the information of the variance of a population is not always available, and statisticians frequently use standard deviation in place of variance. The variance and the closely related standard deviation are measures of how spread out a distribution is. In other words, they are measures of variability. The variance is computed as the average squared deviation of each number from its mean. For example, for the numbers 1, 2 and 3, the mean is 2 and the variance is 1 minus 2 the whole squared plus 2 minus 2 the whole squared plus 3 minus 2 the whole squared divided by 3, and the variance is 0.667. The formula for the variance in a population is sigma squared is equal to sigma x minus mu the whole squared divided by n, where mu is the mean and n is the number of scores. When the variance is computed in a sample, the statistic, that is S squared, that is variance, is equal to sigma x minus m the whole squared divided by n, where m is the mean of the sample, S squared is a biased estimate of sigma squared. However, by far the most common formula for computing variance in a sample is S square is equal to sigma of x minus m the whole squared divided by capital N minus 1, which gives an unbiased estimate of sigma squared. Since samples are usually used to estimate parameters, S squared is the most commonly used measure of variance. Calculating the variance is an important part of many statistical applications and analysis. It is the first step in calculating the standard deviation. The variance of a random variable or distribution is the expectation or mean of the squared deviation of that variable from its expected value or mean. Thus, the variance is a measure of the amount of variation, the values of that variable, taking account of all possible values and their probabilities or weightings, not just the extremes, which give the range. For example, a perfect die when thrown has expected value of 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, that is 3.5. Its expected absolute deviation. The mean of the equally likely absolute deviations from the mean, that is 3.5 minus 1, 3.5 minus 2, 3.5 minus 3, 4 minus 3.5, 5 minus 3.5, 6 minus 3.5, that is 2.5 plus 1.5 plus 0.5 plus 0.5 plus 1.5 plus 2.5 divided by 6, and the value is 1.5, but its expected squared deviation, that is its variance, is 2.5 the whole squared plus 1.5 squared plus 0.5 squared plus 0.5 squared plus 1.5 squared plus 2.5 squared divided by 6. That is 17.5 divided by 6. The variance is 2.9. Another example, if a coin is tossed twice, the number of heads is 0 with probability 0.25, 1 with probability 0.5 and 2 with probability 0.25. Thus, the mean of the number of heads is 0.25 into 0 plus 0.5 into 1 plus 0.25 into 2 is equal to 1. The variance is 0.25 into 0 minus 1 the whole square plus 0.5 into 1 minus 1 the whole square plus 0.25 into 2 minus 1 the whole square is equal to 0.25 plus 0 plus 0.25. The variance is 0.5. With regard to the advantages of variance, finding the variance of a population gives the complete information regarding how the population varies among individuals. Many times, this is exactly what a study hopes to find or infer. By finding the variance, this question is no longer unanswered. And the goal of the study, which is often how to apply the findings, can be expedited. In addition, finding the variance of a population means there will be no error in prediction using formulas that include standard deviation statistics. Future studies can benefit greatly from previous studies that analyzed the same population and simultaneously found that population's variance. This is because even if the population has changed since the first study, as in the case of many types of data, that is, organisms that die and are born, the variance of a population rarely changes to a large degree. This means that the original variance is an accurate estimate of the current variance. This estimate is likely to be a better estimate than the standard deviation that corresponds to a new sample. Thus, the finding of variance allows future researchers to conserve their resources. Disadvantage. It is with regard to resource consumption. Finding the variance of a population is no easy task. If the population of interest is large, then finding the variance will require much time and, as is often the case, money. Because most research is funded by academic institutions or external organizations, the researcher who intends to find the variance of a population must justify the use of resources to the sponsor of the study. This is not an easy task because the larger a population is, the more infeasible such a study will be. Often, the resources that can be spent finding a population's variance can be put to more efficient use. Unconventional. Most applied statistical studies do not actually find the variance of a population. Instead, they often use standard deviation statistics as replacements. Because of this, most of the statistical world does not expect variance to play a role in statistical analysis. One outcome related to this fact is most statistical computer softwares does not take in variance as input. And finally, we will be discussing about standard deviation. The standard deviation measures the spread of the data about the mean value. It is useful in comparing sets of data which may have the same mean but a different range. For example, the mean of the following data is the same, that is 15, 15, 15, 14, 16 and 2, 7, 14, 22 and 30. However, the second is clearly more spread out. If a set has low standard deviation, the values are not spread out too much. Standard deviation is most widely used measure of dispersion of a series. The standard deviation, that is SD, is the square root of the mean of the squared deviation from the mean of a distribution. The SD is a measure which, unlike the variance, expresses dispersion in the original scores. The formula for computing standard deviation is, for a population, sigma is equal to root of sigma x minus mu the whole squared divided by n. Whereas for the sample standard deviation S is equal to root of sigma x minus x bar the whole squared divided by n minus 1. Now, let us have some simplified calculations for the variance and standard deviation. The formulas in the preceding sections are called deviation formulas because in each case the specific deviations of individual values from the mean must be determined. Alternative formulas which are mathematically equivalent, which do not require the determination of each deviation, have been derived. Because these formulas are generally easier to use for computations, they are called computation formulas. The computation formulas are population variance sigma squared is equal to sigma x squared minus capital N mu squared divided by capital N. Population standard deviation sigma is equal to square root of sigma x squared minus capital N mu squared divided by capital N. Sample variance S squared is equal to sigma uppercase x squared minus lowercase n into x bar squared divided by lowercase n minus 1. Sample standard deviation is calculated by S is equal to square root of sigma x squared minus lowercase n x bar squared divided by n minus 1. Here is an example. Here are the amounts of gold coins 5 pirates have, that is 4, 2, 5, 8 and 6. Now, let us calculate the standard deviation. Calculate the mean. X bar is equal to sigma x divided by n, that is x1 plus x2 plus x3 and so on divided by capital N, that is 4 plus 2 plus 5 plus 8 plus 6 divided by 5, and the mean is 5. Calculate step 2. Calculate x minus x bar for each value in the sample. X1 minus x bar is equal to 4 minus 5, that is equal to minus 1. X2 minus x bar, that is 2 minus 5 is equal to minus 3. X3 minus x bar is equal to 5 minus 5, that is 0. X4 minus x bar, that is 8 minus 5 is equal to 3. X5 minus x bar is equal to 6 minus 5, that is equal to 1. Step 3. Calculate sigma x minus x bar the whole square, that is sigma x minus x bar the whole square is equal to x1 minus x bar the whole square plus x2 minus x bar the whole square and so on, that is minus 1 the whole square plus minus 3 the whole square plus 0 the whole square plus 3 the whole square plus 1 the whole square, that equals to 20. X minus sigma x minus x bar the whole square is equal to 20. Step 4. Calculate the standard deviation. S is equal to root of sigma x minus x bar the whole square divided by n minus 1, that is square root of 20 divided by 5 minus 1, and the standard deviation is 2.24. The standard deviation for the amounts of gold coins that pirates have is 2.24 gold coins. Let us discuss about the advantages and disadvantages of standard deviation as measure of dispersion. It gives you a better picture of your data than just the mean alone. It can always be calculated. Standard deviation is a meaningful characteristic of a set of observations. It takes every observation into account to express the scatteredness of observations. It lends itself to computation of other stable measures and therefore is a prerequisite for many of them. The average of deviations are around the mean. Majority of the data within one standard deviation are above or below the mean. It is not expressed in squared units, so makes more sense descriptively. And the disadvantages would be, it doesn't tell you the full range of the data. It can be affected by outliers, that is, rare numbers much smaller or larger than everything else in the data set, so as to give a skewed picture. It is more complicated to calculate and it is influenced by extreme scores.